Hello and welcome to another video on Zero Trust Networks. In this video, we will look into the way devices are trusted in Zero Trust Networks. The requirements for better understanding of this video would be to watch the first three videos on the Zero Trust Network series in that order. Let's get started. Trusting devices in a Zero Trust network is extremely critical. It is also an exceedingly difficult problem as well. Devices are the battlegrounds upon which security is won or lost. They're everything that means to a network. Most compromises involve a malicious actor gaining access to a trusted device. And once the access is obtained, this device can no longer be trusted and to attest its own security as well. So when that is done, it's game over. In this video, we will discuss many systems and processes that need to be put in place to have sufficient trust of the devices deployed in a zero trust network. We'll start learning with how devices gain trust in the first place. When a new device arrives, it is typically assigned an equal level of trust as that of the manufacturer and the distributor. You think a Dell laptop with a Windows 10 image right out of the store is trustworthy to be in the network? How sure are you? Just by looking at the hardware details or software version is not sufficient for the device to be trustworthy. There are two basic principles that exist to start with trusting devices. First one, golden images. No matter how you receive your devices, you should always load a known good image on them. Software can be hard to vet. It makes good sense to certify an image for distribution. Second, the device still needs to be able to identify itself to the resources that it is attempting to access. This is typically done by generating a unique device certificate that is signed by your private certificate authority. When communicating with the network resources, this device presents its certificate, which is signed. This certificate proves not only that it is a known device, but also an identification method. Using details embedded in this certificate, the device can be matched with data from the device inventory, which could then be used for further decision making. We have a device, we need to provide it a signed certificate. It is not as easy as it looks. Every certificate comes with a private key. How do we store this key? A malicious actor should not be able to access it even if the device is compromised. One way is to give access to it only for highly privileged users like system admin. But what if the attacker can do an access elevation? This method will be futile, obviously not desirable. Another way is to encrypt the private key to prompt for password every time you want to use it. Well, this works for devices which are used by the users, like workstations or mobile devices. But what about servers? It isn't going to work. There's nobody to enter the password each time. For this exact reason, we have TPMs, Trusted Platform Module. You see those in every switch, controller, access points in the network. TPMs provide a secure area in which cryptographic operations can be performed. They provide a limited API that can be used for asymmetric encryption keys where the private key never leaves the security module. Whereas the OS cannot access the private key stored in the module, and so can the hackers. It cannot be stolen. When a new device is to be provisioned, the operator will generate a certificate for the device. He will send a CSR on the device's behalf to a private CA. Once the CA creates a certificate and sends the certificate, it is forwarded to the device. This is a manual system wherein operator has full control over the entire process. But do you really think it scales? I don't think so. Imagine I have a lot of servers. How do you generate certificates for each of these servers? We may need an automatic provisioning system that could distribute certificates for all these servers. If the provisioning is automated, but it is still human driven, it makes a lot of sense to allow the human driving that action to also authorize the associated signing request. Having a human involved every time is the best way to prevent unauthorized requests from being approved. But you see, humans are not perfect, right? They're susceptible to fatigue and other shortcomings. For this reason, it is recommended that they be responsible for approving only requests that they themselves have initiated. It is possible to accomplish provisioning and signature authorization in a single step through the use of a temporal one-time password, TOTP. In this diagram, you can see the TOTP is provided by the operator to the provisioning service. The TOTP can be provided along with the provisioning request and passed through to the signing service for verification. This simple yet strong mechanism allows for human control over the signing of new certificates while still imposing only minimal administrative overhead. Since a TOTP can be used only once, a TOTP verification failure is an important security event and needs to be flagged. It's pretty easy to be monitored as well. If you want to fully automate provisioning of new hosts, like an auto scaling setup, TOTP would not make much sense, right? How do we do it? Then, how exactly are we going to provide certificates to each of them? Signing a certificate is an operation that requires a great deal of trust. Just as with other zero trust components, this trust must be sourced from somewhere. So, what are the choices we have? Like an operator, a resource manager, the image, or the device. A human is an easy and a secure choice, but since it is static, it's a non starter in this schema. The resource manager is a privileged position. It has the ability to both grow and shrink the infrastructure as it has complete right over what to do and is likely able to influence its availability. It can use this position to either directly or indirectly authorize the signing of a new certificate. It might be desirable not to grant this ability wholly to a resource manager. Credentials can be baked into an image, but this too is not advisable because it places too much responsibility on the image store. In a similar way, HSMs or TPMs can be leveraged to provide a device certificate that is tied to the hardware. This is better than baking the credentials into the image. One good way to mitigate these concerns is to require both the resource manager and the trusted image device. Generic authentication material baked into the image can be used to secure communications with signing service and can serve as a component in a multifaceted authorization. As an example, we could consider this for authorization. A registered TPM key or the image key. TPM has a storage root key that is responsible for all the signings. A valid and correct IP address. A valid TOTP generated by the resource manager. Expected certificate properties like common name and other details. By validating all of these points, the certificate signing service can be relatively certain that the request is legitimate. How? A resource manager alone cannot request a certificate, right? Since it does not have access to the hosted provisions, the most an attacker could do is to impact the availability. Similarly, a stolen image cannot request a certificate as it requires a resource manager to validate that it has provisioned the host and expects the request. This way, we could secure the certificate signing request and the certificates and knowing that they are valid. Now that we know how to store identity in a new device or a host, we have to figure out how to validate that identity over the network. X509 is perhaps the most important standard we have when it comes to device identity and authentication. One of the coolest things about X509 is that the public private key pairs it uses to provide identity that can also be used to bootstrap encrypted communication. For a certificate to mean anything, it has to be trusted. A certificate can be created by anyone. So just having one with the right name on it doesn't mean much. A trusted party must endorse the validity of the certificate by digitally signing it. A certificate without a real signature is known as a self-signed certificate, which can be used for testing purposes. It is the responsibility of the registration authority, a role commonly filled by certificate authority, to ensure the details of the certificate are accurate before allowing it to be signed. In signing the certificate, a verifiable link is created from the signed certificate to the parent. If the signed certificate has the right properties, it can sign further certificates, resulting in a chain. The certificate authority lies at the root of this chain. By trusting a certificate authority, you're trusting the validity of all the certificates signed by it, all across in all of the chains. The primary capability of an X509 certificate is to prove identity. For that, it leverages two keys instead of one, a public key and a private key. A public key is always distributed and the private key is held by the owner of the certificate. The owner can prove that they are in presence of the private key by encrypting small piece of data which can only be decrypted by the public key. This is known as public key cryptography or asymmetric cryptography. X509 certificate contains a wealth of configurable information. As you can see in the code snippet, one of the fields is called the subject. The subject field stores information about the owner, which in our case is a device or host. Traditionally, fields like organization and organizational units are exactly as they sound. But in data center applications, they can be repurposed to provide richer identity. The example shows one approach where O is mapped to the environment and OU is mapped to the role of the host. Since the certificate is signed and trusted, we can use this information to make authorization decisions. The application of X509 to device authentication in a zero trust network is immense. You would see certificates all over zero trust networks. If the private key is stolen, the whole device authentication thing is a sham. How do you make sure the key is safe and secure? TPMs are the way. A trusted platform module is a special chip that is embedded in a computing device. It's called a crypto processor. These chips are dedicated to performing cryptographic operations in a trusted and a secure way. They include their own firmware and often thought as a computer on chip. It provides facilities for cryptographic operations. It excludes interfaces for retrieving private keys. That is exactly the security we need without ever exposing secret keys to the operating system. Instead, they're just bound to the hardware. TPMs generate and store what is known as a storage root key or an SRK. This key pair represents the trust root for the TPM device. Data encrypted using its public key can be decrypted by the originating TPM only. So, how do we use this whole thing? We know that asymmetric operations are very expensive and thus not suitable for encryption of large pieces of data. As you would have seen that most bulk encryption never use public private keys. They always use symmetric encryption. Thus, in order to leverage TPM for bulk data encryption, we must reduce the amount of data that the SRK is responsible for securing. An easy way is to generate a random encryption key, encrypt the bulk data using symmetric encryption like AES, and then use the SRK to encrypt the resulting AES key. At the end, you would get encrypted data encrypted using an AES key generated from a private key. Inventory management involves the cataloging of devices and their properties. Maintaining these records is equally important for both servers and client devices. One of the great powers of a zero trust network, it knows what to expect. An inventory database is a major component in realizing this capability. Huge amount of information about what to expect can be generated from this data. Things like which user application should be running on it, what locations we might expect to be in, or even the kind of operating systems are all pieces of information that can be used to set expectations. This is all good for devices in data center, but how do we take care of the client facing systems? In order to address the wide nature of the client facing systems, we need a slightly different approach. One way to do this is to simply allow global access to the service and protect it with mutually authenticated TLS, forcing the client to provide a device certificate before it can communicate with it. The device certificate can be used to look the device up in the inventory database and then determine whether to or not to authorize it. The advantage is that lots of systems support mutually authenticated TLS. But what if the device doesn't have a certificate? How to provide one? How to ensure that we don't engage these clients yet? There has to be some untrusted communication after all. What comes before authentication? Tricky question. The very first connection from a new device is a precarious one because you have not trusted the device yet. After all, these packets must be admitted somewhere, and if they are not strongly authenticated, then there is a risk. Therefore, the first system that a new device contacts needs a mechanism in which it can authenticate the initial contact. This arrangement is commonly known as secure introduction. TOTP provides one such means. The method through which an operator passes a TOTP code to a provisioner in order to authorize a certificate request is a form of secure introduction. What makes a good secure introduction system? Single use. Credentials and privileges associated with introduction should be for single use, preventing an attacker from compromising and reusing the key. It should be short lived. Credentials and privileges associated with introduction should be short lived, preventing accumulation of valid but unused keys. And it should be from third party. Leveraging a third party for introduction allows separation of duty, prevents the introduction of poor security practices, and alleviates operational headaches. The natural progression is that the longer a device is operating, the greater its chances of being compromised. It would always start with high amount of trust, and over a period of time it starts losing because of the activities and the amount of time it spent on the network. This is why the device age is a heavily weighted trust signal. For this reason, rotation is very important. If your infrastructure is on cloud, perhaps a device is a host name. In this case, rotation is easy. All you have to do is to tear down the instance and build a new one. But if you're running physical hardware, this prospect is a little more difficult. Reimaging is a good way to logically rotate a device. It is fairly low level operation and it will succeed in removing the majority of persistent threats seen in the wild today. When it comes to managing client devices, the story changes quite a bit. Reimaging a client device is extraordinarily inconvenient for users. For example, I don't want to change or upgrade my OS on my phone. That's my choice to make. So, what options do you have on the clients to rotate? Local measurement can be one of two types, hardware based or software backed. The hardware backed measurement is more secure and more reliable, but is limited in capability. The software based is less secure and less reliable, but it is practically unlimited in its measurement capabilities. TPM is a kind of hardware backed measurement. Software backed local measurement involves some sort of an agent installed on the endpoint, which is used to report health and state measurements. This could be anything from a managed antivirus to a policy enforcement agent. But what if the host itself is compromised? It would send whatever information it would want, possibly falsifying information in order to conceal the attacker. This is not possible with remote or passive measurement since a completely different system is determining the health of the host in question. Traditionally, remote measurement is performed as a simple vulnerability scan. The system in question will be periodically probed by a scanning device which observes the response. The response gives some information away, like what operating system it runs on, what services it might be active there, and maybe what version of the services. The scan results can then be cross-referenced with known bad signatures like malicious software or vulnerable versions of the legitimate software, etc. Detection of known bad signatures can then influence the trust of the device appropriately. Unfortunately, vulnerability scanning comes with the same fundamental problem as local measurement. It relies on the interrogation of the endpoint, which could be easily manipulated by the attacker on the endpoint itself. Software configuration management is a process of tightly controlling and documenting all software changes. The desired configurations are typically defined as code or data and checked into a revision control system, allowing changes to be audited, rolled back, and so on. As you can see in the diagram, you have different subsystems in an SCM process. All the data would be stored in SCMDB. Beyond auditing and strict change control, configuration management can be also used as an agent for dynamic policy configuration. If a node can get a reliable and trusted view of the world, it can use it to calculate the policy and install it locally. We can leverage the wealth of data provided to us by the CM agents. We can calculate the trust score and write policy against a lot of host attributes. As you can see from an example, the attributes that we could see here are the description, the version of the software installed, the build version, the name of the software, and other details like BIOS revision, ROM size, etc. These host attributes could all very well be used to calculate the trust score and write a policy against it. This lists some more attributes that could be used. Vast majority of the data available to the CM systems is self-reported. This is critical to understand since a compromised machine could potentially misrepresent itself. Any of these devices could send wrong information about itself. The CMDB simply stores it. These can lead to complete compromise of the zero trust networks. The attributes to look for: device type, a role of the device, an IP address, and the public key. These attributes are considered critical because they are often used in making authorization or authentication decisions. If an attacker can update the device role, for instance, perhaps they can coerce the network to expose protected services. It is extremely important to be wary of critical parameters. Extra care needs to be taken while validating or updating these parameters. What are the trust signals that would help us trusting a device? The time since image. Over time, the likelihood that a device has been compromised increases dramatically. Imaging a device ensures the contents of the hard drive match a known good configuration. In the moments immediately following the image restore, tremendous amount of trust exists in the device, as only the hardware or the restore systems itself would be able to taint the process. It would still take time for attackers or malicious software to creep in and reduce the trustworthiness of the device. Over time, this trust wears off as the system goes through prolonged exposure. Historical access. Devices which have not been seen in a while are more suspicious than the ones that come and go frequently. Frequency can be analyzed to understand if a resource is being suspiciously overutilized. Location. While network location is typically something we aim to not make strong decisions on with regard to the zero trust model, it still provides reliable trust signaling in many cases. For instance, a device authentication attempt from Europe might be pretty suspicious if we have authorized the same device in the US office just a couple of hours prior to that. Network communication patterns. For the devices that are connected to the networks owned by the operator, there is an opportunity to measure communication patterns to develop a norm. Sudden changes from this norm are suspicious and can affect how much the systems trust such a device. One example might be shutting down the database access to a particular web server because the web server began making DNS calls for hosting providers on another continent. That's all for this session. In the next session, we will be looking at users, authentication, when to authenticate, how to authenticate, group authentication and authorization, and trust signals of the users. Thank you for watching. Bye bye.